Hey there, it's Horner, and we're going to look at a problem. This problem is 2008, number 2, and it has to do with force and it has to do with springs, so we'll do a little bit of both. The first thing they want us to do is calculate the force that the spring exerts on the 2 kilogram block. So to do that, first thing we need to do is let's go ahead and do a diagram for the entire just our system. So we've got a dot for A, we've got a dot for B. They are connected by a spring, but let's go ahead and do them individually. So for this first one, we have a force going to the right, and we know that that force is going to be a tension. We also have a force going to the left, and that is also tension. It's the same. So it's the tension in the spring is really what we're looking at. There's no force going to the left because this is frictionless. It does say that here, horizontal frictionless surface. But we have a force going in this direction, and that force would be the force of this 4 Newton pull. So now we've got those two things. Let's go ahead and do a sum of the forces. So the sum of the forces for block A are going to be equal to the mass of A, and we're going to multiply that times the acceleration of A. They're going to accelerate at the same rate once you get them going. And then the sum of the forces on B should be equal to the mass of B times its acceleration. So now we've got both of those. The only force we have going on letter A, remember, so here's A, here's B. The only force on A we know is tension, so that's equal to M times big A, MA times A. And for B, this one we've got a force going to the right, F, minus T. So here's F, T is going left, so we say minus T, and that's equal to M big B A. Let's go ahead and substitute in for T this MAA. So we know that we can take, since that's T, this can go right in here. And at this point we can say F minus M big A times A should be equal to M times B, MB times A. And now we have the force is equal to MB times A plus MA times A. So there's our equation so far, and they want the force. Now, before we can do that, we've got to find the acceleration of the system. So let's go ahead and solve this for A. We know that A should be equal to the force over MB plus MA. And some of you may be trying to figure out where I got that from. Really simple. We just took this equation and we factored out the A. So we're going to say the force is equal to, then we're going to say A times MB plus M, it's not wanting to work, MA. And then we made it into that equation. So at this point we can go ahead and put all our numbers in. So we've got 4 newtons over 2 plus 8, and 2 plus 8 is 10, so we end up with a acceleration of 0.4. So this is definitely, oops, it's going to be 0.4, so I'll make a better point there, 0.4 meters per second squared. But they don't want to know, what the acceleration is. They want to know what is the force that the spring exerts. So I keep trying to make this 2 and it just doesn't want to work. There we go. So at this point now we need to just say the force of the spring, so Fs here, is equal to the mass of A times its acceleration, since that's the only thing really that we had. So the force of the spring should be equal to Ma times A. And so the force of the spring is just equal to 2 times 0.4 meters per second squared. So here we end up with 0.8 newtons. And that would be our final answer for part A. That part's actually worth 4 points. And the first point would be just getting the initial equation. So that initial equation, I think, is probably the one that we have right here. And then you get a point for this equation and making sure you fill it in right. and get the right answer. Then you get an equation for just finding the substitution here, and then finally get another point for that answer. Okay, so let's go on to the next part, which is part B. And this part isn't too bad. It says calculate the extension of the spring. So remember, whenever we want the force of a spring, boy, this just doesn't work, that should be equal to the K value times X. We're going to leave this positive. And now we're going to say that X is equal to the force of the spring divided by K. And so the force of the spring, they told us, was that we found out was 0.8 newtons. And we're going to divide that by the spring constant, which is 80 newtons per meter. And when you're done, you should get a stretch, or remember, it's a change in position for the spring, of 0.01 meters. And that is how you do part B. So this pen's not being nice today. Okay, so that part's actually just 2 points. You get 1 point for doing all this work down to here, and then you get 1 point for the answer. At least you did that year. For letter C, we'll go on down and look and see what it's got. It says now the system is pulled to the left. So the only difference is our force is going to the left. A lot of other things don't really truly change much here. But they want to know, is the magnitude of the acceleration greater than, less than, or the same as before? And it should be exactly the same. Now, a lot of you think, well, shouldn't it be bigger because you get a smaller mass here? No, because remember, the mass that we're pulling is this entire thing, and the mass is not changed. So as long as you say that in this spot, so you want to just say mass total is the same, and then you'd have to say so the acceleration is the same. They want to then know, is the amount the spring has stretched greater than, less than, or is it the same as before? And for this one, the stretch is going to be greater. And the reason it's greater is because the 2 kilogram mass is less than that 8 kilogram mass. And so when you pull it to the left, you get more resistance from that 8 kilogram mass. And so that's kind of what you end up with for that one. And you don't want to, you don't need to do part E. So we're just going to leave that part off. I really think that's just about it for that problem.